Hello everyone. Today's lecture is the module over the principal ideal domain, second series. I want to view in this lecture T-Cyclic decomposition theorem in the linear algebra as the module over the principal ideal domain. This is the theorem which is learned in the previous lecture 10. This theorem is important because we will use this theorem, repeatedly use this theorem again. So let me remark this theorem. And another important theorem which I've remark is the if we consider we will deal with the principal ideal domain, and every principal ideal domain has unique factorization domain. And in prior to talk about our main top lecture, let's remark the element OA. OA is consisted here, and some others called this is annihilator. What is the annihilator? The definition of annihilator is the collection of R. In this case, R is a ring. R is a ring, and S is just subset of R. So S is not to be a special addition, such as R is not to be a subring, just a subset of the R. Then the collection of R, what is the collection? For all, we choose for all element in S such that Rs is equal to 0. Then we can say that this is guys annihilator. So some people say skip the notation R, just to say ANN S. So ANN S. Some precisely the small character and the large character ANN is slightly different, but in this case I want to say this is ANN S. What is the S is small letter is the which if we pick the element in S. Okay. In this case, when we considering the definition of the annihilator, OA is clearly annihilator. The reason is clear. In this case, R is the ring and S is just a fixed number, but it's one element. So S is the singleton set. Because singleton set is one element fixed, all element is just A, and when the definition of the OA is the collection over here, just OA is the annihilator. So this is also can write ANN A. In this case, A is just one singleton set. And this is the important slide part if we important key if we understand the T-Cyclic decomposition theorem into the R module sense. In this diagram, is R, RA, R quotient of A is familiar with the previous lecture 10. In this case, just R just change the FT, and A is the element in A is just the A additive group, and V is just to change the V. This is a vector space. In this case, we can understand FTV then. This is the polynomial, collection of the polynomial. So FT, if we choose the FT in FT, this is the collection of the, we can choose the FT, then this is consists of AN, XN. If we consider degree n polynomial, this is non-zero element, and a1, an minus 1, xn minus 1. In this case, the parameter, because the parameter of t, an, tn, dot, a1 t plus a0. If we consider degree n polynomial, this is non-zero element, and for all coefficient is the field. Even if the coefficient is contained the field, ft does not be field. This is just a ring structure. Okay. And ftv means just ftv. This form ftv. And we can understand, also we can understand ft is the ring and v is additive group goes to v, and we can choose ft and v goes to ftv. If we define this here, I want to say talk about this, that here. ft, I want to say the v, collection of the v is in fact actually left module of ft, I would say ft with unity. It's v. Okay. In the notation, with definition of the, R module, v is the left module over ft with unity. Let's check. We can check easily this property. This exercise. And anyway, the important thing in this lecture, an important turning point is here to understand our main topic is ft module is the another new protagonist in this lecture. And let's see the theorem which is related to cyclic. In this case, the observable point, remarkable point is that this is principal ideal domain and prime. The first, the principal ideal domain, if we consider the principal ideal domain, we studied OA. What is the OA? Is the collection of the R in R such that RA is equal to 0 is clearly ideal. But in this case, because this is the R is the principal ideal domain, this absolutely expressed for some singleton set. I don't know which element can be eligible, but however, there exists for some element in R such that OA is expressed this guys here, because this is the principal ideal domain, and if if the principal ideal domain, R is the principal ideal domain, every ideal is expressed the single generated form. And second, P is a prime. But this is R is not integer or natural number. This is just abstract ring. But in this case, we can define prime, which is emulated to the integer, such as prime number. Okay, this is the clearly follow the properties of the prime number. Just this definition translate into the abstract ring. Okay. Then these two properties are satisfied. Remarkable point, because this is principal ideal domain, this OA is expressed clearly the single generated form. Okay. And the interesting point, if we change the R, just put FT. So on the FT module, this is interesting thinking. For example, if statement A changed into this case, first F I V F I T F I T. This is power of the I goes to V is 0, then OV, the annihilator is also, some say this is annihilator V is generated. In this case, P is the irreducible polynomial. Okay, we in the abstract ring is the P is the prime into the polynomial. In case of the polynomial, the prime is translate irreducible polynomial. So the annihilator V is expressed P, this is power, so P I X for this is J. P J X, or this is many people, this is better expression, P X J. Okay. Where is J is from 0 to I. As similarly, we can translate V as the FT module's word. Let's see the proof. The first, I want to say OA is expressed this form. Check this form. But clearly, important point, because OA is the ideal and R is the principal ideal, OA is absolutely is expressed some element in R. And by the assumption, PIA is equal to 0. By assumption, PI is equal to 0. This means PI is P to the I is contained OA. The definition of the OA. This is it, and this is R. But note that every principal ideal is unique factorization domain. So R is only contain this prime and does not express other prime. So R is only expressed this P and this unique factorization domain U, where is J is from 1 to I and U is a unit. This means OA is written as R, but R is the PJU. And because U is unit, just written as PJ. So our first statement is finished. In order to prove second statement, let's negate the conclusion. This means, suppose there exists J such that J is smaller than I, such that P J A is equal to 0. This means, by the first condition, OA is clearly expressed PJ with this condition is clearly satisfied. Then PJ, this is P J by the assumption OA is equal to PI, P to the I is contained in PJ. This is I, this is J. This means PJ can divide PI, even though J is smaller than I. Even though this case, PJ can divide PI. This is clearly contradiction. So we can prove this statement. So when considering the previous theorem, this means if the OA is the principal ideal consists of the PI, where is the P is the prime. This means I say when we multiply I times, so PIA is equal to come back to 0. This is clearly the definition of satisfies the definition of the cyclic. When I times comes, this goes to the identity. But if the I is PI, it does not come back to 0. Okay. And note that this is when we give the natural homomorphism from R to RA, and this is the ideal, and OA is indeed kernel phi is checked in the previous lecture. This is the isomorphism. So this is the cyclic relation. This is also cyclic relation because this and this is isomorphism. So we can check. This is also cyclic. Then the cyclic submodule RA generated by A is said cyclic of order R. It is also interesting. We can change into the idea of the FT V, because we can consider naturally think of the FT module. So we can say in this case OV is the in this case P irreducible polynomial PI, I say just PI, okay, PXI. Of course we can think this is the corner, but we can also we can think this is annihilator. Annihilator. But of course it is also same A and N. Some element in this case V in A. Okay. And this is also because this is just changed the R, just putting the FT. This is also cyclic. This is cyclic submodule. Then we can find a common denominator between the cyclic submodule and the cyclic subspace. When you consider all of the condition is given, R is the principal ideal domain. Under this condition, we can catch if we can check the RA is the cyclic submodule. Okay, the cyclic submodule RA generated by A is said to be cyclic of order R. We can say this RA is written as the RA, where is the R is in R. And we can understand, just put R is FT, then you can say FT V, and FT is the polynomial ring. Of course, FT polynomial ring can be the principal ideal domain, and such cyclic submodule RA or FT is generated by A, or the vector element V is said to be cyclic of order R. When you consider this idea in the T-Cyclic submodule, let's consider the GVT. GVT is the subspace of the vector space V. So this is subspace, and this is the vector space. This T-cyclic subspace means the basis V, TV, and T square V, TRV generated W. This means if we can choose the element in W, and W is the generated V, this means because in identity, so this is A0 I V and A1 TV, and AN T R V. This W is generated by this basis IV, TV, and TRV. And we can write this is A0I and A1T and finally ANT R V. We can say this looks like a polynomial. So we can say this is just changed FTV. So we can write the element W is written as FT, F large TV. So the element, we can say we choose the element W, but this is written as W is because it's equal to here. We can say large FT V and FT is contained FT. But in this case, large T is the linear transformation. Like we can think linear transformation as a n by n matrix. This comes to the matrix. We can find this when comparing this and this. We can find the common denominator, the correction of this, and the name is called T-Cyclic subspace by generated by V. In this case, generated by V, and this generated by V. And this is polynomial ring. This is also polynomial ring. And this is cyclic, and name is cyclic submodule and T-cyclic submodule. Let's see the example of the T-cyclic subspace in the linear algebra. But I'll explain using the commutative diagram which I referred to T-cyclic subspace this here. Using this concept, I will explain the T-cyclic subspace. Let's see this here. Let's consider T is the linear map R4 to R4, which is the map is given A. This is the matrix form. We can consider, and then consider characteristic polynomial. Originally, many authors use the PT to express the characteristic polynomial, but I will use the P is the means in this lecture irreducible polynomial, and I will use this notation as irreducible polynomial. Instead, I will use the CT, characteristic polynomial, and this means the definition of a characteristic polynomial is A minus Ti, and indeed, if you tedious process calculating, we can get this is T minus 2 to the 4. This is the characteristic polynomial, and then we can consider FT using I refer to commutative diagram FTV, and we can see the CT is clearly contained in FT, and we can see FT is the quotient of annihilator V. annihilator. What can be the annihilator in this here? This is clearly homomorphism. This, if we can naturally give the map phi from ft to the ftv, this is clearly homomorphism. And indeed, if annihilator v is equal to corner phi, then we can deduct this is the isomorphic relation to these two objects. Okay, then Ct is clearly the element of the polynomial. And another remarkable point is the Cayley-Hamilton theorem. And if we substitute, this is during the proof, just directly substitute A instead of T is not a right proof. It is important point of the proof of Cayley-Hamilton theorem. But anyway, the result is if just comes to the matrix A, then this result is clearly zero matrix. This is the result for Cayley-Hamilton's theorem. And we have no problem if we just instead T instead of the large matrix T. So there is this diagram. Just change the value T, large Ft, just change T as the matrix from Ft V and F large T. This T is the linear map. So this comes to the matrix A annihilator V goes to here. Okay. And remarkable point is that we studied the linear algebra. If the characteristic polynomial is given, there exists the minimal polynomial MT, where this polynomial is divided the characteristic. So characteristic polynomial divides the minimal polynomial such that MT can be also zero. In the sense of the matrix form, just in the case of the we can consider matrix. This comes to the matrix. So MT large T is divided CT such that M large T can be the zero matrix in the sense of the matrix form. Okay, then indeed in this given the characteristic polynomial, there exists minimal polynomial. We can directly find MT. This is T minus 2, but it is 1 less than 3. Instead of T comes to the matrix MT, this is T minus 2I third to the third can be the zero matrix. Okay. Directly you can find this minimal polynomial, and this means when consider this diagram, T minus 2I3 and FTV means, this means again we can interpret T minus 2I third. Look at this diagram, V can be the zero matrix for any vector space element. Okay? This means we can consider t minus, in this case, t minus 2I third is equal to corner phi. And because of the space is too shabby, I deleted it from the information. We'll consider this point and yeah, many more polynomial sense. Okay, then remark this relation, this row relation. What is this important? When we consider this theorem, I introduced the theorem. This is a similar form. More precisely, this yellow part is here. Okay. In this case, P is correspond t minus 2I. Then we consider the polynomial sense is the t minus 2, and t minus 2 is clearly irreducible polynomial in the sense of the irreducible polynomial, and VA corresponds to this V. So this is the zero matrix. This means from here we can deduct OA. OA I referred is the here. This is the it is better to read the OV. OV is annihilator V. Okay, is expressed as this is multiple form. This is principal ideal form. So bracket is outside the bracket means the multiple of the polynomial instance is multiple, and P comes to 2 T, because we consider this here large T matrix I and third square. It comes J is 2/3. And we can also we can check this the property. If we substitute another exponential such as 1 and 2. Okay, if it is indeed substitute t minus 2I square is not can satisfy zero matrix, but come to substitute third from this part more than third, t minus 2I to the third is 0, and t minus 2I to the 4 is zero matrix. Okay. And another remarkable point, this is the corner. Okay, corner phi. As I mentioned, this is the corner phi. We can understand annihilator V annihilator is indeed come to the OV, and this is the t minus 2I third. This is the multiple of t minus 2I to the third. Because this is the corner phi, we can say this is the isomorphic ft quotient of the t minus ei to the third of this is isomorphic to ftv. Continuously, now let's consider this diagram again. Okay. Okay. Type mistake is rather than, because this matrix is given, this is better. A minus 2I to the third is the better. And we can consider this vector space in element V. Remarkable that if we consider corner phi, this is because this is the corner phi. A minus 2I to the third V is zero matrix for all element in V. Okay? This means for any element comes to this here, this can be the zero. So at the time I substitute E1. This is the standard matrix in this basis. This basis is standard matrix. This consists of naturally, obviously, 0, 1, 1, 1. Any element can spew out zero matrix, but I choose the standard elementary matrix. Okay. Then this is clearly zero matrix, and we can construct. My object is to construct the T-cyclic subspace. This means G E1T. Is it notation more? Okay, GVT. Consider this copy this here. Okay. GVT. V comes to the E1. T is the given matrix. This is linear transform matrix. Okay. Then, when you consider the linear algebra concept, the maximal degree in this polynomial, third, decide the dimension. So the subspace of GE1, T is clearly has dimension 3, and this is clearly three bases. Okay. The construction of the basis is easy. If we consider basis E1, I said the basis is generated I copy this here. Okay. The basis is construct V, TV, T2V, and TRV. Okay. So the basis is E1, TE1, because this is the matrix A, so AE1, and finally A square of E1. If we consider this is the basis of the T-cyclic subspace, if indeed calculate this here, this is E1, I will say this is 1, 0, 0, 0, and the AE1 result is 2, 0, 0, 1, and finally A square to the E1 is 4, 0, 1, 4. Indeed, if we really checked whether this can be the basis of the T-cyclic subspace GE1T, we can check the definition of the basis, or this is better to the elementary. I forget the name. Just if we try to elementary transformation 1, 0, 0, 0, 2, 0, 0, 0, 1, and 4, 0, 1, 4, and if try the elementary transformation, we can deduct 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So transforming elementary elementary form. We can check this is clearly basis of the given subspace. Okay, so this is can be the basis. So this given vector element, this guy's generated GE1T. Okay, subset of the V. Remarkable point is that because of this equality equation, this vector space to generate this subspace is not unique. So if you just any element, no problem. If you start from any element, just a little complicated 31 start, we can generate it also vector space subspace G. For convenience, I'll put this is the A1. G A1T is also subspace of given the vector space, in this case R4. Okay, so the important point, the vector element is not unique. We can first, in this case, we can choose for any vector space element, choose and then construct GE1T subspace of the R4. And the most intriguing point is here. I'll say GE1T is clearly the subspace of the R4. And this has three bases. And the remarkable point, R4 is clearly this dimension is 4. So if the one dimension is at one basis, if we can one basis added from G1, the subspace. So if we construct new subspace of the R4, we can find these guys. We can clearly R4 is generated by GE1T and direct sum of blah blah. The result, the blank comes also the T-cyclic subspace. But we can find whether this is element A2. Okay. The form of the blank is clearly this T-cyclic subspace because by the theorem. Let's see this theorem. I will not prove this statement, but we can intuitively infer the existence of the subspace. Okay, let's read the theorem. A is the modulo of the principal ideal domain such that P to the n A is equal to 0, and P, this situation is, we can compare this situation. I copy this here and copy this here. This situation is similar. A minus 2i is the in this case, P is the prime, okay? A minus 2, T minus 2 is the irreducible polynomial. So, in this case, T minus 2 is non-zero, but T minus 2 to the third is 0. If we made in the matrix sense, A minus 2i to the square is clearly non-zero, but A minus 2i to the third is clearly 0. Okay, matrix, in this case matrix. Then claim is here. If A is correspond Okay, in this case, A is corresponded FTA, so this is the corresponded to vector spaces. Okay, then R is corresponded to the polynomial FT. So this means if A does not generate the RA, this means you can change the here. Okay, RA corresponded to FTV. So anyway, the vector space does not generate the FTV. Then there exists some non-zero element B in such that RA intersection RB is the empty set. No, not empty set. This is only the zero element. This means you can understand V. I will pick the E1, okay? E1, T1, and A1. I always hesitate. A1 and A squared to the 1. This guys generated clearly subspace of the G E1 T. This is because this is third dimension. Indeed, this does not generate R4. Okay. Okay. In this case, V is corresponded to, okay, this is R4 when using the previous example. So this is generated R4. Clearly, this is 3 bases. This is 4 bases. Then there exists non-zero element B. The B is corresponded to actually the B corresponded to here. VT, such that RA, RB is equal to 0. Intersection, these guys are 0. So this means G1T to begin it, I cannot assure this form is generated these guys, but indeed the result is here. Okay, and this is clearly 0. And indeed this and second theorem means indeed is clearly the subspace of R4. The second property says this is the subspace of R4. Finally, this because this is the non-zero and this is subspace of R4, this is the clearly when considering the dimension, this is the one dimension. So by this theorem, you can check R4 is expressed as G1 E1T direct sum. The definition of direct sum, each set intersection of each set can be only 0. This is B1 B. In this case B T. By below this theorem, we can finally deduct this here. This is come to the so-called the T-Cyclic Decomposition theorem. I'll say the T-Cyclic Decomposition theorem is here. Let V be the finite dimension of the F vector space and T is the home FVV. This means T is just a linear map. Linear map or linear map is one-to-one correspond to the matrix. Okay. And home, because of the home V to V, this is n by n square. If the dimension V is the n, this is clearly corresponding to n by n matrix. And V is direct sum of the cyclic T invariant subspace. Important point is the invariant. The invariant means T, if W is the subspace of the vector space, TW is still the subset of the element. So this means V is clearly decomposed T invariant subspace. The form is the G V1T T GVNT. And the remarkable point is that each member of these fractions is clearly T invariant subspace. I will not explain this theorem, but in the linear algebra, it already exists the primary decomposition theorem. So all of the vector space, firstly decomposed all element is decomposed element is clearly primary T invariant subspace of this. Each member is the T invariant subspace. This is the reason of primary decomposition, and each element is generated by the element V1, Vn. This is the result of the T-Cyclic decomposition theories. Okay, so this is the combination of the primary decomposition theorism and the T-Cyclic decomposition theorism. So, vector space, finite vector space, any vector space is given, the vector space is decomposed in this following form. And the primary decomposition warrant this each fraction is the T invariant subspace. Another important point is the uniqueness of the T-cyclic decomposition theorism. So, if we decompose these elements W1 to Wn and another vector T-cyclic decomposition U1 to Un, then the result is n is equal to m, Wi is isomorphic to Ui. The important point is that this is not the same, but this is just isomorphic relation. But the number is the same. I'll typo, this is the m. So if we suppose V is the two T-cyclic decomposed two types of the T-cyclic decomposition, then the number is originally same, and each element is isomorphic for each I. Even though the order would be changed, but we can find one is isomorphic to something. Important point is that this is isomorphic. The reason is that when you consider, we started from the important theorem is that the method, the way of the T-cyclic decomposition is up to isomorphism. This is the result of the uniqueness of the T-cyclic decomposition theorem. So, if vector space V is decomposed two types of the T-cyclic decomposition, I will mishap. This is the large M. So, suppose two decomposition, which is the different of the element fractions 1 to n, this is the 1 to m. Then, even though if we suppose this here, finally the number of the fraction is the same, and each is isomorphic. The important point is that the point is made G, E1 and T, if we suppose this here, but this so the element E1 to En is actually the same number. If this generated number vectors element, this vector element GE1, and if we choose the G A1, A, and T, okay, this number vector space element to decide the W1, Wn is finally the number of the vector element is the same if we consider another element because this theorem. Okay, so this number is the same, but in this case, the vector type of the vector, the element of the vector is not unique. We can just guess this from here. In this point, I started because a minus 2I to the third v is 0, and this is isomorphic to here, okay, we can start it with, if we generated GE1t, in fact, for any element, instead of En, any element come to the here, we can generate GB, this subspace. Because when considering this part, the element of the vector is not unique, but the number of the element is clearly same. The number of the element, even though the type of the vector's element is the different, but the number is the same. For this reason, this relation is in fact not the same, but is isomorphic. So back to the previous example, I clearly generated GE1t, okay? But in order to generate whole space R4, because this is 33 dimension, another element is required. But when consider T-cyclic subspace, because this is the one dimension, so if we, for convenience, I put the B1, and B2 is clearly one basis. So this is easy because we can just find, because we know we need to A squared to E1. Just one element, find one element, this corresponds IE1 clearly. I blah blah blah. I blah blah blah. And the way is here is just the element does not depend on these guys, because easily, because this has four bases, always we can pick the vector space element which is not depend on these guys. Okay, what is the better? For example, if we consider, okay, because this 0, 0, 0, so we can just find 1, 0, 0, 0. Let's consider, suppose to this guy. If we try to check this, this is clearly independent of this another element. Okay, and G, indeed this is clearly, in fact it's E2, GE2. T is generated alpha. Of course, we can choose instead of E2, we can choose another element. For example, 0, 3, 0, 0. It is no problem. Okay, so anyway, we can choose the element, find the element such that this R4 is generated T-cyclic subspace. And the last slide is the lecture is that In order to explain the another type of the T-cyclic decomposition theorem, I will give the example, I will analyze this example, and then introduce the another type of the T-cyclic decomposition theorem. Just as I did earlier, let's consider R3 is decomposed to T-cyclic subspace. If we R3 to R3 is the linear transformation is given, first let's consider characteristic polynomial. Just calculate a minus ti. The result is t minus 1 and t minus 2 to the square. This is characteristic polynomial. And next we can find minimal polynomial. But important point, always characteristic polynomial divides the minimal polynomial. So the minimal polynomial contains always absolutely contains this coefficient, the t factor t1 minus t2, and the index is depend on your evaluation. But we can find the index is just 1. So the minimal polynomial is t minus 1 times of t minus 2. And then let's draw the diagram, commutative diagram, ft and ft v and ft quotient of annihilator v. And because this is the minimal polynomial means t minus I, when you consider the matrix sense, t minus I times of t minus 2I, and substitute the vector space V is always zero matrix of all V in V. Let's consider standard basis E1 first. 0, 1, 1. So if we consider annihilator E1 is correspond, substitute annihilator, delete it here. I substitute E1. Okay, why so wrong? E1. In this case, this is subspace of the R4. Okay, and annihilator E1 is consist empty minimal polynomial, and clearly G, E1 and T is isomorphic to large FT quotient annihilator E1 is empty. I will directly write this here, t minus 1, t minus 2. And okay, this is principal ideal form, and I will put mt as f1t. Okay, f1t. So we can write ft as the f1t. Okay. Okay, if we calculate the vector space is consist of E1, T1, and if we calculate this element, E1 is 1, 0, 0. So E1 is 1, 0, 0. And the second is 5. I forgot this here. 0, 0, 0. Just here. Minus 1 and 3. This generates the subspace of the R3. So R3 is G E1 T. And okay, and the next is to generate another element of these guys. Of course, it is no problem. We can check if we can choose A2 for convenience. A2. This is A2 is not dependent of E1 and TE1. Okay, then we can generate it. This R3 is generated. This guy is generated R3, but I will construct this here. R3 is G1T, and when construct this, I'll choose the special element of this here. And note that this originally this is the isomorphic to FT quotient of annihilator, but I put the annihilator is the FT1T. Okay, and I will choose element this here. We remember the characteristic minimal polynomial is consist of t minus 1 and t minus 2. And I will investigate this here. T minus I V can be zero matrix, or T minus 2I V can be the zero matrix. Okay, in this minimal polynomial, I will investigate this solution of V. In case of this former case, because determinant T directly calculate determinant Ti just non-zero. This means the solution is clearly 0, 0, 0. And this, if we consider, this is no interesting point here, but interesting point is to find the solution here. To begin with, if we investigate t minus 2i, this means just in the diagonal component, just subtracting 2, so 3, 2, 2, another is the same. Minus 1, 2, 2. But interesting point is already revealed. This and this is the linearly dependent. And indeed, if we try to elementary transformation, we can directly get this relation. 1 minus 2, 2 over third, 0, 0, 1, and 0, 0, 0. This form, we can say this determinant is t minus 2i is just 0. Okay, and from this form, if we find the solution of this matrix T minus EI, if we directly find the solution is consists of 2, 0, 1. Okay, and 2, 0, 1 vector, the basis of this basis is E1 standard basis, and TE1 is the 5, 1, 5, minus 1 and 3, and this, if we pick 2, 0, 1, this each vector is the linearly independent. So for convenience, I just put the elementary matrix is just A1. This just put A1, and if we put this A2, then this is G A2T. But important point is that is here. This position can any vector element which is independent of these vectors come to here. Okay, but if we just this guys comes here, we can express this is ft, because this 2.1.0 is the solution of this here. Ft quotient of, and for convenience I put this t minus 2 is the f2t, and mt is the f1t. This is here. Okay, and the remarkable point is that when we pick this element A2, and this is isomorphic this form, and F1 can divide F2. Okay, we can observe this point when we pick the special element A2, choose here. So okay, then and let's see the another description of the T-Cyclic decomposition theorem. Previously, I explained Chinese remainder theorem, and this is already apply generally. We can describe the ring, but because fx is clearly polynomial ring, this is description of the polynomial case. So each Ri just change Fix. So let F1x, Frx be pairwise relatively prime polynomials. This means each polynomial, the index is different, cannot divide each element, and fx is the multiplication of each polynomials. Then fx quotient of fx is isomorphic to these guys as fx modules. And let's see T-Cyclic decomposition theorem. The invariant factor T is uniquely determined. That is, if we have two composition, this is typo. If we suppose there is two decomposition exist, where is annihilator is given, and this means it is better to understand fi divide fi minus 1 for all I, and this is similarly g, because this index is the n, okay, that's the notation problem. F1 fn minus 1 divide fn for all n, and this means gm divide all of gm minus 1 can divide gm for all m. Okay, then this is the same. In fact, the uniqueness of the decomposition is well known above the theoremism, but important point is that V expressed as fx v1 direct sum fx vn, but this form is all fraction is isomorphic to fx quotient annihilator v1 and fx is annihilator vn. Above case, we can say this form, okay? When say this form, in fact, this is fx. Where is annihilator v1? Is f1 f1t, and this another form is quotient of ft2. And remember that what is the f1 and ft2? I deleted this here. f1 is t minus 1 t2, and ft2 is t minus 2. In this case, we can check f2t, okay, f1t precisely divide f2. Okay, we can observe this property. And we can say it's just f1t and it's f2t, and by Chinese reminder theoremism, this is isomorphic to fx quotient f1t times of f2t. What is this? Yes, this is t minus 1 times of t minus 2 to the square, t minus 2 square. This means, again, I'll describe t minus 1, t minus 2 square. This is the characteristic polynomial. So we can understand this. Quotient of V is, in fact, we can understand V is isomorphic fx quotient of the characteristic polynomial, and this is here, and from the Chinese, conversely, by the Chinese reminder theoremism, we can decompose this here, and this is isomorphic here, and this is here. So if the element, we can decompose the specific element V1, which is isomorphic to ft quotient of annihilator form. We can get another type of the cyclic decomposition theoremism.